Welcome to Chemical Process Safety. In this video, I'm going to show you how to use a flammability diagram, and this is going to be important for how we try to avoid flammable mixtures. So this is obviously a triangle, and you can represent mixtures of three things still in two dimensions on such a triangle. If you're in separations class, you might have seen one of these diagrams already. But the reason why this works is this is a two-dimensional shape, obviously. It's on a piece of paper. So I have three components which in this case are going to be oxygen, nitrogen, and fuel. And the reason why we are separating oxygen and nitrogen, which we wouldn't normally do, those are the two components of air, is because again, we're trying to remove the leg of the flammability, the fire triangle for oxygen, for the oxidizer. So anytime you have three components, in general, you must specify two of them in order to specify the system, composition of two of them. And the reason for that is once you specify the composition of two, the third is then set because remember they have to add up to 100%. So any point within this diagram, let's just pick that point just for an example. If I read off the composition of that point, I would say draw a line up to here for this would be 40% oxygen. I always like to label them on the vertices. But you might not always see that. I can label it this way for fuel. So once I've specified 40% oxygen, 50% for fuel, the remaining 10% must be left for nitrogen. You can see that's the case from drawing down to the nitrogen axis. Now, I think the first thing I want to do for these diagrams is showing you where the air line is. So the air line is a conceptual depiction of what would happen if we mixed fuel and air. Describes all possible mixtures of fuel and air. And the way we draw that is we find where pure air is. So with 0% fuel, 79% nitrogen, 21% oxygen. So pause the video and see if you can point out to yourself where that would be. And air is going to be down there, right? So 0% on the fuel axis, 21% on the oxygen axis, which is up here. So I'm following this line diagonally down to the southeast, and 79% nitrogen. Pure fuel is going to be up here, the top vertex of the triangle. And all possible mixtures of fuel and air. This is something generally true in ternary diagrams like this. Anytime you have two things that you're mixing, what you can do is you could find the two compositions on that diagram, which I've already done, and then you draw a straight line in between them. So I'm going to do that and we'll see what happens. Okay, that was a disaster. I was trying to find how to draw a straight line, but I ended up just freehanding it in. I'm trying out a new tablet. So this is supposed to be a straight line, and we can pick any point on that line, or a good exercise may be to yourself, what would happen if I mix, let's say, I don't know, 80 moles of air plus 20 moles of fuel. Again, you can prove this to yourself. You can work out the material balances. And I encourage you to do that. And what you would find is I can do this faster by just looking at the diagram. So again, the air line, which I've just drawn in, is all possible mixtures of fuel and air. And if you're just estimating, which is okay for now, you can estimate how far along the line you go based on the relative proportions. So 80 moles of air, 20 moles of fuel. So it's 80% air. So I'm going to go 80% along that line towards air. So it's going to be about there. Again, if you want to be more precise about it, you'd actually measure that. I theoretically have a ruler to do that, but I couldn't figure out how to get it to work. Or what you could do again is work out the material balance. So you could say for nitrogen, for example, the nitrogen material balance would have 80 times 0.79 because that's nitrogen was 79% of the air, and then equals 100 times composition of N2. So we'll call that YN2. And and then you'd work out whatever that is, and then you'd plot that point for the nitrogen axis. And you would find that you would land there every time. So here's a more general way to algebraically describe what the airline is. We'll start by saying, as must be true, that the compositions of the three components have to add up to 100. So if I take the composition of oxygen plus the composition of nitrogen plus the composition of fuel, those must add up to 100. We'll work in percentages because, again, that's what the book does. I have another constraint here that YO2 is going to be 0.21 over 0.79 times YN2. Right, that is what regular air is going to be. So then what I can do is I can substitute, plugging in this expression for YO2, and what I'll get is 100 equals 1 plus 0.21 over 0.29. We'll factor out the YN2 and add the Y fuel. And then what I want to do is solve for N2 in terms of Y fuel. The reason, again, why I'm doing this is I want an algebraic expression. So it's, you never need to know what the algebraic expression is, quite honestly, but it might help some people. If you don't understand why, I can just simply draw this line on the graph and it works. So again, what I'm doing here is I'm expressing the composition of nitrogen as a function of the composition of the fuel. So if I solve for YN2, I will get 100 minus Y fuel over 1 plus 0.21 over 0.29. So again, I want to make the point that this ternary diagram is simply a tool for performing material balances very quickly. Anything you could do with material balances, you can just do using the techniques that you learned about in MEB. But doing them on the ternary diagram is going to be a little bit quicker. The next thing that we might do that may be of interest is looking up what the LFL and the UFL were for our fuel. So remember, this is going to depend on what fuel we have, and the flammability diagram is very general. It doesn't specify what the fuel is. But if we were to specify what the fuel is, so let's say, just for example, pick ethanol as the flammable thing, I can go to the back of the book and look up what the LFL and the UFL are, and then I can plot them on this diagram. So for ethanol, it happens to be the UFL is 19%. So I could find 19 on the fuel axis, just below 20 there, and plot it. This is the UFL for ethanol. And the LFL is 4.3%. So about halfway, a little bit less than halfway between 0 and 10. This is the LFL. And I can do this because remember, the LFL and the UFL are the percentages that are in air. So again, the airline is all the mixtures of fuel and air. And the LFL and the UFL are the percentages of the fuel when mixed with air. So that's why I'm finding where these compositions are and where they intersect with the airline. The next thing I want to do is look up the LOC for the fuel. This again stands for limiting oxygen concentration. And this is the concentration of oxygen that is required to combust. So below the LOC, we will never have the hope for a flammable mixture. Not the hope, but the hazard for a flammable mixture. And in the back of the book, I found that for ethanol, the LOC is 10.5%. So I want to plot this. This is a line of constant oxygen concentration. So keeping it constant. So 10.5% oxygen, no matter what the other two components are, is a line that is going to be perpendicular to this axis. So something like this. I'm drawing this more at 10 rather than 10.5, but that's just my bad drawing skills. So I'm just going to follow this line here, and this is my LOC line. Once again, any point on this line is going to have 10.5% oxygen and varying with the other two things, nitrogen and oxygen. The next thing I want to do is extend my LFL point and argue that the LOL is equal to the LFL. So, yeah, this is supposed to be a straight horizontal line, and I said it was what? I said it was 4.3%. So I'm kind of using that as a guide. Whoop, let me get this better. And that looks pretty good. And so what I'm doing here is I'm working towards working out the flammable zone, if you will. I'm trying to work out what mixtures are going to be flammable, what mixtures are going to be safe, and that is going to help inform my decision for inerting. Because when I inert a vessel, I want to make sure I drop the oxygen concentration low enough. And you might say, well, why don't you just drop the oxygen composition below the LOC because that's the point where you'll never have a combustion. Remember, this stuff is all expensive, right? So we want to be efficient. We want to remove the potential for a hazard, but we also don't want to spend money unnecessarily with buying pure nitrogen and pumping that nitrogen. That can all add up. So we want to be efficient with how we use our resources. The next thing I'm going to do is you see I've made an intersection here, and that is going to be a key intersection there. If I connect this point with the LFL and then I extend that point. So there's a couple different ways that you can do this. It really doesn't matter. I tend to just like to extend it straight. It really doesn't matter how it extends because we won't be working in that region of the graph anyway. Anything that is between those 2 points, let's switch back to red, or anything that is within this entire zone that I'm shading in right now is called the flammable zone. Red shading is flammable zone. You can look in the book, by the way, for there's a couple different ways that they recommend that you draw in the shape of this line. But again, we won't be working with this region of the graph. And the conceptual reason for that is as you work this way, that is increasing the oxygen concentration, which you would never do in the context of chemical process safety. So you might do it if you were doing lab experiments or something. But for our purposes, we are always going to be to the right of the airline because that is going to be removing oxygen. So I'll wrap this video up here. And again, just the take-home messages are that this ternary flammability diagram is a tool to perform material balances. And by plotting out this fire triangle, you can, there's the flammability zone. You can quickly determine whether or not a given mixture is flammable or not. In the next section, we're going to do inerting, which is figuring out what percent of oxygen you would need to have in order to not have a flammable mixture. So see you then.